So welcome everyone online. Thank you for coming to this next EC Bayes seminar. It could be the last one for the year. I'm not sure. Maybe we can sneak another one in like we did last year. But it's great because today we have Sebastiano Grazzi from University of Warwick in the UK presenting on PDMP samplers and some new exciting work to do with those. Sebastiano, I'll leave it over to you to get started.
Thank you, Josh. So, as you were mentioning, today's talk will be about piecewise deterministic Markov processes, PDMPs, with some boundary conditions to try to target measures which come up with non-Stardom Bayesian problems. And this is going to be an overview, so I will not go into technicalities. And essentially, what I will talk about today is my work of the second part of my PhD, which is joint work with my previous supervisors, which are Joris Bierkens, Frank van der Meulen, and Maurice Schauer, and some follow-up projects that I'm currently doing with my current supervisor, which is Gareth Roberts. Okay. So the presentation is structured as follows. I will start introducing ordinary PDMPs. So ordinary PDMPs, they are used to target measures which have a density, a smooth density relative to the Lebesgue measure. So that they cannot be used for other classes of target measures. And then I will move to PDMPs with boundaries. And PDMP with boundaries can be used, for example, when the reference measure is not a Lebesgue measure, or when the density is not always differentiable, for example, or is not always continuous. Okay. I will talk about three different types of boundaries. The first one I informally called sticky floors. And these boundaries, they allow PDMPs to be used for variable selection, essentially, and for sparse Bayesian problems. And the paper I'm referring to is already out on arXiv. It's going to be published very soon, and it's called the Sticky PDMP Samplers. And if you're interested in this topic, I'm also pointing to the other work from Matt Sutton, which is called reversible jump PDMP samplers for variable selection. They have many overlapping ideas, and I think if you're interested, you should look at both. Then the second type of boundary I informally called soft and hard walls. And they are used for example, when the target density is not always continuous. And here the motivation and the example I'm trying to work out is trying to sample the latent space of infection times in epidemic models. And this is, as far as I know, it's a very difficult problem for MCMC. It's known that MCMC have usually poor mixing, and they don't scale well with the dimension size. And the dimension size here correspond to the population size, which can be high. So by using PDMPs, we try somehow to tackle both problems. And the paper I'm referring here is not available online. It's still in preparation, you will hopefully it's going to be released soon online. There is another paper which is more technical, more theoretical about PDMPs for discontinuous densities, piecewise smooth densities, which is already online, and you can look at it. And finally, the last type of boundary, I call it teleportation portals. Essentially, this allows the process to not be continuous, and which sometimes is key for the process to be ergodic. So we just introduce teleportation portals that allow the process to jump in space. Okay. Now, let's start with some notation. My parameter space is denoted with X, and it's going to be in RD. We have a prior measure mu0 and a log likelihood. This is in the Bayesian framework. And with these terms, then we can derive the posterior measure. Now, as usual, when using MCMC methods, we want to construct a Markov chain which converges in distribution in some sense to the target measure, the posterior measure in this case, and in such a way that we can use a law of large numbers and we can estimate the integral relative to the posterior or relative to mu with integrals, essentially path integrals of the Markov chain. And in this framework, as usual, the constant of proportionality C is assumed to be unknown. Now, this is an illustration of what are PDMPs. PDMPs are some specific Markov processes which are continuous time Markov processes, and they are conceived and also simulated in continuous time. These are ordinary PDMP samplers. So the target measure of these processes, of these samplers, has a density, which is smooth, which is continuous relative to the Lebesgue measure. And all the PDMPs have a momentum variable, so have a velocity, and they have this peculiar feature to be non-reversible. In particular, they satisfy the skew detail balance, so they are skew reversible. And that's been proved that in some toy setting, in some simple setting, non-reversibility really improve convergence to equilibrium of the Markov process, and also improve the asymptotic variance in the central limited theorem. This is relative to the reversible counterparts. So here you see three different piecewise deterministic Markov processes. So all of them have a piecewise deterministic trajectory, fully deterministic. There is not randomness. And they have a collection of random times. At these random times, essentially, the velocity changes. So the trajectory of this process change. Here in this illustration, I have two different random times. One are called reflections, which make sure that essentially the process is targeting the right measure. And the other one are refreshments. So sometimes they are needed. For example, in the first and the third sampler, they are needed. Sometimes they are not. And they just make sure that the process is ergodic. Essentially, at some times we just refresh completely the velocity in such a way that the process can go from everywhere to everywhere, essentially. And you see that we can play a little bit both with the deterministic dynamics. So in this case, we have curve dynamics, but also with the reflection. So at the reflection time, we can just switch angle in this zigzagging way, or we can have other rules when uneven time happens. These are the three maybe most famous PDMP samplers. Right. In the mathematics, we defined the process in this augmented state space. So it's RD times the velocity space, which is a subset of RD. Then we just define the deterministic dynamics, which are given by a simple ordinary differential equation. And here, the ordinary differential equation, I wrote it in this way. So here I have a function that maps RD to R, which is essentially just it tunes the magnitude of the velocity. So it doesn't change the direction of the process, but it changes the speed, and it's called the speed up function. Right, and if once we define these ordinary differential equations, then we have an associated operator, Xi(f). The second things to define is the frequency of our random times. This is given by a rate, lambda, which is maps the state space E to R plus, and essentially such that the first event time is the first event of an inhomogeneous Poisson process. And you see that the inhomogeneous Poisson process as rate lambda evaluated along the deterministic trajectory. So this is just telling me when is going to be the first event time. And then I can iterate this because the process is Markov. And finally, whenever an event happens, so the clock rings, then we have to tell the process what to do. And this is just given by a transition kernel. For PDMP, as you saw in the animation, this transition kernel just acts on the velocity component. So it doesn't change change the state x, but only the velocity v. All right, we can make this PDMP more and more complicated by having multiple events. For example, we can define multiple events, lambda i's, and every event is triggering is different. So we have an associated kernel for this event, and we can stack all them up in this way. So the sum of the rates will be our lambda rate, and the kernel will be just a weighted average. And finally, we have this triple. So we have Xi, which is defining the deterministic dynamics, lambda, the frequency of our random times, and Q is the kernel. And this is we can stack all them up with this operator A, acting on functions. And this is denoted the extended generator of the Markov process, and is somehow a central tool for PDMPs. So when we study PDMPs, we look at this object. We look at this object mainly because we want to understand what is the invariant measure of the process. And for PDMPs, for any Markov process, the invariant measure mu is an invariant measure of the process if this integral relative to the measure mu is equal to 0 for all the functions which are in a certain class of functions, which is called the domain of the extended generator. This is a necessary condition. And here, since the process is not reversible, we cannot use a detailed balance argument to prove, to show that IMCMC has a certain invariant measure. Okay. Now, let's move to PDMPs with boundaries. By the way, if you have any question, please stop me. If you're interested on the formal setting, I'm referring to, for example, to the original book of PDMPs, which is written by Davis, or a recent paper on PDMPs with boundary conditions. In this talk, I'm simplifying a lot the setting. So I'm assuming that we have a target density mu on RD. And we define just boundaries. Boundaries are D-1 dimensional piecewise smooth manifold. And in R2, in this illustration, they are just piecewise smooth lines, essentially. So in this setting, we have to define entrance point in the boundary and exit point in the boundary. These are points where the process hit the boundary and points at the boundary where the process leaves the boundary. You can see it from the arrows. Note especially that there are two copies of the boundaries, right? And what we just have to do in this for PDMP with boundaries is just to define kernels which maps points at the entrance of the boundary to points at the exit of the boundary in such a way that the process always stays in its state space, essentially. And this is going to be a recurrent thing during this talk. Now, as I said, the first boundary I will talk about, I define them sticky floors. I define them sticky floors because the process, whenever it hits this boundary, it will stick at the boundary for some time, for some random time. And these turn out to be useful for variable selection and for sparse Bayesian problems. If you don't know, so in the Bayesian framework, sparsity means that you have prior information that some coordinates of your parameters might be exactly 0. And this happens, for example, for variable selection or when you want to regularize your solution and in other situations. Now, in all this setting, the prior and the posterior must be supported in these lower dimensional subspaces of RD, where we take RD and we fix some coordinates to be exactly 0. And the measure must have positive values for these subspaces. Now, if you think of, I don't know, a Gaussian measure or some measure which have a density relative to the Lebesgue measure, this property is not satisfied. So the usual, well, the most popular prior measure used for variable selection is called the Bierkens lab, and has this form. So you see that the reference measure is not anymore just Lebesgue, but is a mixture between Lebesgue and Dirac. And in particular is the product of D component. So under this prior, with probability Wi, the parameter is exactly 0. And with probability 1 minus Wi, under this prior, the parameter is distributed according to this density, pi. All right. And remember that we want to estimate this integral relative to the posterior with a path integral. So if our measure has positive values in these subspaces, then also the process needs to spend positive time in these subspaces. So you can just see that the ordinary PDMPs, they don't work because they don't spend any time in these subspaces. Right, and the idea we came up with is pretty simple. So you look at every coordinate. Every time one coordinate passes through 0, it spends some random time at 0. It sticks at 0 for some random time. And after that, the coordinate will just be released and it continues its motion. This is the simple idea. If you do it for every coordinate, that then you can explore the subspaces that we wanted to explore. And something that I still have to say is how much that we have to understand is how much time should the coordinate stick at 0. All right. Again, from illustrating, I'm moving to the mathematical framework. Here, as I mentioned before, we have to split the boundary with 2 components. So the boundary here is 0 for every coordinate. So we have a 0 minus and a 0 plus. And we define this entrance or hitting set where the process hits 0. So the process can hit 0 minus either with positive velocity, or it can hit 0 from above with negative velocity. And then we just define a transfer mapping which move the coordinate from 0 minus to 0 plus and vice versa. And finally, the very nice thing of PDMPs with boundaries that many things remain the same. So you can define the extended generator in exactly the same way you define the extended generator for ordinary PDMPs. But what you have to do is just to restrict the class of functions to be the same class of function as before, but at the boundary, essentially here we are just telling that the process must stop. So there is no green component, there is no deterministic dynamics, must wait exponential time with this rate. And then after waiting, we'll jump on the other side of 0. This is just saying this. All right. The rigorous proof of the invariant measure of the process is a little bit technical and involved, and I will not discuss it in this presentation. But what I will just say is that the necessary condition that we wanted to check to show that the target measure is the one that we want to sample from, we can check it with invariant measure mu, which has this form. Essentially, it's funny because so without this extra red bit, it would be the standard target measure that ordinary PDMP would target. But now we have an extra bit for every coordinate, which is this direct measure. And you can see already the similarity with spike and slab priors. In particular, actually, spike and slab prior and smooth likelihood, they fall within this class of targets. So you can use it when you have spike and slab prior. But it's not the only class of priors that you can use. And also in the latest version of the paper that I think was updated last month, we also prove ergodicity. And again, it's quite nice because the proof of ergodicity really relies on ergodicity of the classical ordinary PDMP. So it was actually easier than what I expected to prove ergodicity. And if you prove ergodicity, then you know that this measure is the unique target measure of the process. Now, turning to the illustration or the application of PDMPs, here I have one. In the paper, we have several applications. I put this because, from my perspective, it's quite impressive. So we have the statistical problem is just an image observed with white noise. So the ground truth, the image, is this, here you can see it in this little rectangle. So essentially the ground truth is black, essentially almost everywhere. And black pixel means the pixel being equal to 0. And this is the observed picture. Okay. What we want is we want to denoise this picture, so we want to enforce with a prior that well that most of the pixels are 0, so we want to enforce sparsity. And here we are not using spike and slab because so the likelihood essentially doesn't correlate the pixels with each other. But we know that neighboring pixels should be correlated, right? So we enforce also smooth solution by adding an extra bit here, which is just a Gaussian density, with this gamma matrix being a Laplacian operator, so a 3-diagonal matrix. And yeah, just to come back, the impressive things is not really the problem, is the dimensionality of the problem. So here we have 1000 pixel by 1000, so the dimensionality of the problem is 1 million. Right. This is the output somehow. On this left half of the picture, you see the posterior mean, just estimated by running the PDMPs. On the right half, you see the error of the posterior mean with the ground truth. So you can see that there is essentially no error whenever the image is black. And this is just a section of the trace of the zigzag of the PDMP that we run. Essentially, is so these are two coordinates which are correlated, and this is so neighboring pixels and which are non-zero. And this is the trajectory of a pixel which is 0. So you see that it sticks at 0 for most of its time. Right. Now I'm approaching variable selection from a PDMP perspective. So I'm not an expert on variable selection, but for what I could see in the literature, I could somehow compare with the competitors, let's say. Something unique, I think, of PDMPs is that they have continuous trajectories, while all the competitors, they usually are discrete Markov chains. Having continuous trajectories has a limitation because we cannot jump between not neighboring models. And with this, I mean that, for example, if the process is exploring R2, and we don't want to explore the axis, which it would be a neighboring model, but we want to jump into, for example, the point 0, 0. The process will never hit the point 0, 0 with probability 1. So it will never be able to jump to this model. And therefore, there is a limitation. The nice feature of PDMP is that they don't need any proposals for moving between models. So everything is kind of automatic. While for what I have seen, all the competitors, they need a very particularly, so some proposal kernels which needs to be chosen very carefully. And yeah, so also, of course, the PDMPs, maybe I didn't stress this out, but the PDMPs, they use the gradient of the target density for exploring the state space. So that means that the exploration of the models is informed by the likelihood. And they don't need to evaluate base factors. Okay. And this is just a loose comparison, but in our paper, we have other more formal arguments with mixing times and complexity of the algorithms and some comparisons, also with some numerical applications. Okay. Now, some remarks before moving to the next boundary. So here, as I said, the dimensionality is huge, and it's not straightforward to run a MCMC in such a high dimensional setting. The trick of PDMPs is that, so a sticky PDMP, or zigzag in this case, I use a particular PDMP, behaves locally as a lower dimensional ordinary PDMP. So essentially the complexity of the algorithm is driven by this lower dimensional process. So it's true, we had a process which was defined in 1000 dimensions, but essentially it was never, it was always lower dimensional than that, way lower dimensional, like maybe 100,000 dimensions. And that really helps the complexity of the algorithm. If you want to do something similar with discrete Markov chains, it's going to be much harder because the discrete Markov chains, they jump in space. So the probability of hitting the boundary is 0, essentially. As I said, it does not require the proposal kernel to explore models. So what I've seen also in the literature is what people tends to do is to okay, there are no MCMC that are able to deal with spike, which are direct measures. So what they do is to approximate the spike, the direct measure, with a continuous density. And then you fall back to the ordinary setting where you have a density relative to the Lebesgue measure. But you can see that this way of proceeding has some limitations. First of all, because then the problem becomes is 1 million dimensional, so would be the original size. So you don't gain any advantage by introducing sparsity from a computational point of view. And plus, there are also numerical problems, because if you approximate your spike with a continuous density, then and you use a gradient, for example, a gradient-based method, then the gradient will explode at around 0, because you have a lot of mass around 0 due to your prior, and discrete Markov chain will just have numerical problems whenever the gradient explodes to infinity. Something which is nice to have is that you also have non-reversible jumps between models in this framework. Other remarks is that I will not talk about this in this presentation, but if you are interested also in the setting where you have big data and also high dimension, then the PDMPs, they allow to use subsampling. And subsampling means that for every iteration, the gradient of the log density, usually if you have IID observation, that it will be the sum of terms of n terms, where n is the sample size. So if n is large, then at every iteration, you have a high complexity to evaluate this gradient. And with PDMPs, you can use a subsample similar to stochastic Langevin diffusions. But the nice feature of PDMP is that it's still unbiased. So you don't introduce any bias by looking at subsample instead of the whole data set. So this differs with the stochastic Langevin diffusions. Yeah, and these things I already mentioned it, that we cannot jump between two models. Between not neighboring models. All right, let's move to the other boundaries. So here I illustrate what are soft and hard walls, and also teleportations. So soft walls are essentially boundaries where the process can crosses the boundary sometimes, and it bounces off some other times. While hard walls, essentially, it will never cross these walls, these boundaries. And teleportations are essentially boundaries where the process is allowed to jump in another place, which is again a boundary. So as I was mentioning before, we have a kernel which maps points where the process hit the wall, the boundary, with points where the process leaves the boundary. And this introduces teleportation portals. Right. To deal with this setting, we just need a definition, which is a skew detailed balance. Skew detailed balance is similar to detailed balance. So if you don't have this involution S, then it would be like detailed balance. The involution S in this case flips the velocity. So essentially, this equation says that the process satisfies detailed balance after you revert the direction of the process. If we define signed measure this time, so it's a measure which can also take negative values, which is given by this inner product where n is the normal vector on the boundary, and v is the velocity, s is the speed up function, and these are just the target measures from where you want to sample from. This is for the position, and this is from the velocity. Now, then you have an informal theorem, which is if the process is satisfy the skew detailed balance condition relative to this measure, then the PDMP with boundary partial E admits mu times R as an invariant measure. It's quite, so it maybe looks not easy, but it's quite a easy condition to be satisfied. And actually, we can just straight away write down just an algorithm. So we can write down a kernel which takes point at the boundary and maps with other points on the boundary. So just a kernel on the boundary. And then we have acceptance rejection step where similar to metropolis listing. So with this probability, the new point will be accepted. If you accept the new point, then you have to draw a new velocity, which essentially would, you can see it as a rotation. So you hit the boundary with a certain angle with the boundary, and then you have to leave the boundary, preserving this angle somehow. Otherwise, if you don't accept the new point, then you will just reflect at the boundary. So you will draw a new velocity, which is such a way that the process is leaving the boundary. And note that this acceptance rejection step has a S in it, so which is the speed up. So you can actually tune this speed up in such a way that sometimes you can just tune it for having probability 1 to jump on. So you speed up and in this way you compensate for if there is a jump in the likelihood, for example, or something else. So you can you can use the speed up for having sometimes for having acceptance probability 1. All right. Now, okay, running out of time. This is a very interesting problem. Is again an epidemic model, which is called SINR. Is essentially the model which is modeling individuals which during emerging infectious disease, where the individuals start being susceptible, then they become infected. Then they are notified, so then you know that they are infected, and afterward they will be removed. Okay, and here the population size is N. So the way the people becomes infected is according to inhomogeneous Watson process. This is a standard for this class of models. So essentially, every individual has a infectious rate. So it becomes infectious with a rate lambda I for individual I, and this is given by the pressure given by the neighbors of this individual. So it's just a sum of terms where each term is essentially if the neighbor is infected and the individual I is susceptible, then it's positive. If the neighbor J is notified, then this term will be lower because probably he will stay home and he will not try to infect you, and it's 0 otherwise. And then the other assumption is how the individual goes from infected to notified, and we just say that this happens according to just distribution capital F. This is the delay between infection and notification. Right. So the notation is tau for the infection time, tau star for the notified, and tau circle to for removed individuals. Here is the model simulated forward. So on the y-axis you have individuals, and on the x-axis you have the time until observation time. So here observation time is 5. You start with the one individual being infected, and then the infections propagates. What I want to stress here is that in this model, we don't assume that we observe the infection time, but we only observe the notification time, and of course the time where the individuals are removed. So there's essentially the solid lines in these plots. The dot lines are not observed. Okay, so you can see that the model has a huge latent space, which is the infection times. And we want to use the PDMPs to sample, to explore this latent space of infection times. Now, to improve the scaling of the algorithm, so essentially instead of sampling the infection time, we sample the minimum between the infection time and the observation time. That means that if an individual will be infected in the future, I don't care because at the observation time it will be susceptible, so it will be a healthy individual. In this way, essentially the scaling of the algorithm is driven by not the population size, but the infected population size. And there are settings in which the infected population size is small compared to the population size, so it's convenient to do that. And you can see that by having also this minimum between a random variable and capital T, then the measure that we want to sample will have a direct measure at capital T. So then essentially we introduce some sticky floors in this setting, which are, for example, this coordinate, blue coordinate is sticking at capital T most of its time. And when it's sticking a capital T, it means that it's going to be infected in the future. It was not infected in the past. And essentially, yeah, so this is how you should interpret a coordinate that is sticking at capital T. Now, the other thing that I haven't said is that the likelihood has many discontinuities. So it's essentially we defined a boundary, a soft or hard wall for every discontinuity. You can straight away see that if an individual is notified, for example, here there's the notification time of the individual, which is colored by orange. The infection time must happen before notification, right? So the notification time is a hard wall. The process, the coordinate process will never cross the notification time. And the other boundary, which is straightforward to see, is 0, because then the infection time happens with positive in a positive time. Okay. But all these discontinuities, they happen also whenever, for example, 2 infection times swapped. So instead of the individual I infecting individual J, is the other way around. Then a discontinuity of the target happens, right? So after sampling this latent space, then you can look at the marginals, for example. This is the marginal of the infection times. You can see that these are 4 different individuals at observation time. So individuals that were susceptible, infected, notified, or removed. And of course, if we don't, I know because I simulated the data, but if you didn't simulate the data, these 2 individuals, they look like the same. You don't have any observation for these 2 individuals because they haven't been notified. But you see that the sampler is able to detect that one of them is likely to be susceptible, and one of them is actually likely to be infected, even though it has not been notified. Right. How much time do I have, Josh?
A few minutes, 3 minutes.
All right. Okay. So then I will skip the last example, which is anyway, it's not really Bayesian statistics. Is interesting in statistical mechanics. So yeah, it's just better if I stop with this example. So the concluding remarks for this example is that yeah, so PDMP is actually, it is a general remark. So they can deal well with the boundaries where in this case the discontinuities are points where the gradient is not even defined. And with this framework, you can deal with it very efficiently. In this case, we also combined the 2 different boundaries, sticky floors with walls. Again, as I said, introducing this minimum between the infection time and capital T reduces the algorithm's complexity. And also something that I didn't mention is that PDMPs are also great to exploit conditional independence of the target. So if you have some structure on the target measure, then PDMPs can exploit it to be more efficient. In this case, there is a lot of structure because essentially I'm gonna be infected only according to the status of my neighbors, not the population status. Okay, something that I still have to do is parameter estimation. You would like to combine this latent space with exploration of the parameters. I've been talking about boundaries, but I've been talking about nice boundaries, essentially, where we can compute heating times of the process. If the boundaries are not nice, are nasty, for example, then probably you should compute the heating time numerically, and yeah, it's first of all less efficient, and it's something that I haven't explored so far. And also, I talk about speed up function. I think they are great. They can be used very efficiently, but I didn't manage to understand how to use this speed up function efficiently. So I didn't understand how to tune it. Right. Then let's just stop here. I think the success of the theory, methodology, and also implementation of PDMPs, it really stands from the fact that the PDMPs have continuous trajectories. In this way, the process will hit boundaries. You can define boundaries, and yeah, and everything is very clean and nice. And I'm happy to have any question if you have any question to answer. These are the references.
Thanks, Sebastiano. Any questions? Matt, you want to go first?
Was that me?
That's you, or you.
I think you threw to me. I don't know if I'd raised my hand yet, but I do have quite a few questions, if that's okay. I was wondering, firstly, you mentioned these soft walls, which are really interesting, but when do you get an advantage from using a soft wall instead of a hard wall?
Yeah, so essentially it's implied by the measure. So if you have a jump of the likelihood, for example, from something positive to 0, then the wall will be hard because the process will never explore spaces which are not supported by your measure. While the soft wall is essentially a discontinuity, for example, where the density from being equal to something will be halved, then half of the time the process will cross this boundary, and half of the time will just reflect whenever it crosses to the direction where the density decreases. While when the process crosses the bound, it is a discontinuity in the other direction, it will always go toward the places where the density is has higher values.
Right, that's cool. Yeah, okay, cool. Yeah, and then the other question, I think you mentioned at the end that you weren't so sure on the speed up. And I was writing down, when do you get benefit of the speed up? And yeah, I guess it helps with teleportation though. You could tune it to get an acceptance ratio of 1. Was that?
Yeah, yeah, exactly. It helps with teleportation, but it also helps when you have discontinuities and you want to ignore these discontinuities. So for example, I mean, it's very easy to come up with artificial examples. For example, a bimodal histogram where the density would be this histogram, and whenever there is a drop in density, it's going to be a wall. And if this drop in the density is very high, then the process will almost never cross this wall. By using speed up, then you can cross the wall. You can make sure that you always cross the wall, and you can go on the other mode of this histogram. I'm not sure if I explain myself.
Yeah,
well.
I think that makes sense. Yeah.
But again, it's easy to come up with artificial problems where speed up makes a lot of sense. It's more difficult to come up with real problems where speed up is useful.
Fair enough. Cool. I think Chris had it.
Yeah, there's a question from Chris that I'll just read out. He says, thanks for the talk. What happens when you don't know where the boundaries are and can only tell if you are inside or outside the boundary?
Right. Yeah. So this case is not covered in this talk. Actually, I was pointing out when I made this, so it would be an extension. And I think you need to introduce numerical methods for detecting the boundary, essentially. So it's going to be a sort of a route finder along the trajectory where you want to understand when you're crossing the boundary. This is not ideal because the process is continuous process. Essentially, we don't even simulate the trajectory. We only simulate the times where we hit the boundary or the times where we have reflections. And now, if you want to introduce this numerical method, then you need to discretize in some way the trajectory numerically. So you need to integrate numerically to search for the boundary. But it's possible. It's something that nobody has done so far. So it's an interesting well, extension, which is definitely useful in some cases.
I might have to run and grab the pizza in a second, but I did want to know, and I think everyone did want to know, can you explain a little bit about the teleportation? If you,
right.
you have a few
Yeah, yeah, I think I can stop the presentation with this animation. So essentially here you have hard spheres, which problems, which is this problem where you have these balls which cannot overlap, and you want to sample the invariant measure of these balls, essentially. Since they cannot overlap, essentially MCMC, whenever the two balls they hit, they collide, it will just bounce off, and these can be problematic. For example, if you have many balls, it can be problematic because you will hardly never swap the two balls, the configuration where the two balls are swapped. What you can do is you can artificially so these are the same setting as I explained before with boundaries. These are hard walls in the classical setting, but you can say, okay, instead of only leaving the position trying to cross the wall, which is a hard wall, so it's never possible. I'm just having a kernel which is mapping points from one boundary to another boundary, and they try to jump on space. And in this case, the jumping on space is just trying to swap two balls. And yeah, so if you look at some, for example, here is the inner product, the angle between the two largest balls, which are difficult to mix. You can see that by introducing teleportations, so it is trying to swap the two balls, then the process mixes much faster. And this idea can be, it's actually way more general. I think there are better applications for teleportations, but I still have to figure out. Interesting, probably it could be for for simulating extreme events where you want to jump from, for example, let's say that you want to simulate a Gaussian, but only on the tails of the Gaussian. Then you have a ball and you want to simulate from outside this ball. You can introduce teleportation to move from one point of this sphere to another point of the sphere whenever you hit this sphere. So I think there are other applications where teleportation makes sense. But yeah, I still haven't developed this application.
What condition do you need on the kernel that's defining where, given where you enter the boundary, where you exit, what's the condition that you need?
Essentially, you don't need any condition. So the boundary, the kernel needs to map entrance point with exit points. So you just need to make sure that the point you are proposing. So you can have a kernel, you can have a probabilistic kernel, not a deterministic move. So you can say, okay, I'm sampling from this circle uniformly, and then you have just whenever you jump, there is a drop probably in the likelihood So then there will be an accept and rejection step where the new point will be either accepted, or if it's rejected, then the process reflects and is not able to teleport.
So you use it as if it's like a soft wall, sort of.
Yeah, exactly.
But yeah,
That is precise. Yeah.
Okay. That's nice. Yeah. Lawrence has a question. I have to run away and grab the pizza, but maybe I'll be back before you finish. But if not, so thank you and wrap up for me.
No worries. Thanks, Sebastiano, for the excellent talk. One question before we wrap up. Is this? It's on? Okay, great. Very quickly, is the position of the teleportation, the portals, does that have to be fixed a priori, or can that be defined on the fly?
It can be defined on the fly. Also, the speed up, I think, can be defined on the fly. So according to the drop in the likelihood, for example, that you don't know a priori, depending wherever you jump after teleportation, then you can tune the speed up to increase the probability to teleport. So everything, I think, can be defined on the fly.
That's very interesting. Thank you. Are there any more questions from the audience? There's one in the chat. Hang on. Where is it, Chris? I have to click on it. Raiha, you have a question?
Yeah, sorry, this might be a dumb question, but with the teleportation, do you have any like label switching-esque issues? Or is it not really?
So label switching is related to mixture models, right?
Yeah, just because you have this, like in the balls example, you had them like switching colors and stuff. So I was just wondering if there's any like.
Yeah, so I mean, it's not a
analogs.
problem. Actually, it's a nice feature of teleporting. You can teleport to switch labels, essentially, what I'm saying, because label switching means points in the space where, well, essentially the target, the density has the same value. So you can just switch labels and the likelihood will be the same. And that means that if you propose a label switch, it will be always accepted. So you can jump in space and switch labels in the way you like. And that would be a teleportation move. So maybe I didn't get your question about problems with label switching.
Well, I mean, I guess, well, because you're not really doing like parameter estimation, I guess, right?
Yeah. Yeah,
okay.
I'm not doing parameter estimation. Yeah. So here is really sampling these spheres, the position of the spheres. So it's very artificial. There is not a Bayesian setting for these problems.
Yeah, sure. Okay, thanks.
Matt, you have a question?
Yeah, just to follow on from that, and just for the sake of, you know, making a toy problem more of a fun toy problem, like with the ball problem, is there ever any interest in putting like a probability measure on the space? So balls not only want to be in that constrained space, but like they want to be like at the center of it or something like that. So then they need to bounce off the boundary, and they're also sort of attracted to the center.
So this is actually the problem that I am considering. So I think, yeah, I skipped this part, but these balls, they want to go to zero. They all want to go to zero, but they can't because there are other balls in there, and yeah. And actually, the invariant measure of these configurations is not trivial. So the small spheres they will stay more in the center, and the large spheres they will stay in the outer part. So if you look at the it's I'm not from statistical mechanics. I don't know why they find this interesting, but it's yeah, there are curious problems.
Okay, cool. And so even with it being defined, oh right, yes, your when it hits the boundary, it's not necessarily going to have acceptance ratio of 1 to
Yeah,
10.
the problem of
Yeah.
teleportation is that you propose a move, but you don't know if the new configuration will
Yeah.
be valid or not.
So is this, yeah. So is this one using the speed ups on it?
This is not using the speed up. No. Yeah.
Fair enough.
So what I noticed with the speed up, for example, that you start exploring unlikely configuration. So you will you will jump. You will make sure that you always jump, but then you start going exploring configurations which are extremely unlikely, which is not what you want to do. Yeah, I think you need to be very careful when you use a speed up.
Sebastiano, I have one question as well. I'm sorry if this is dragging out, but I need to know. With portals, very interesting. Does the destination portal need to be known in advance, or can it be randomly selected?
It can be randomly selected. But I think you need to define the boundaries, and so essentially there is a at the beginning. Yeah, so there is this kernel that you want to define. This can be a probabilistic kernel. So this from one point you don't need to deterministically jump to another point. You can, for example, say I want to jump somewhere along these boundaries with some probabilities. I think you need to know where you want to jump. So you need to define these boundaries. Maybe you can look, you can search for those boundaries on the fly, but it's going to be like, these are all extensions that I haven't thought of. And I mean, there will be some numerical challenge to look, to search for the boundaries, or yeah.
So yeah, if you sorry to clarify, yes, if you had say 3 boundaries, could you and you cross one, would you be able to teleport to randomly either one or the other of the remaining boundaries?
Yeah, you can. Yeah, it's very easy to. You can do it without problems.
Fantastic. Thank you. Thank you for your answer.
I made it back. I'm going to guess there's no more questions. I think we've taken up enough of your early morning, Sebastiano. Thank you so much for talking to us so early. I will try to never ask you to give a talk at 6 a.m. ever again, I promise. Yeah, thank you for getting up, and I really enjoyed the talk. You're very thorough and you explained everything very well, so thanks so much.
Thank you for inviting me. Thank you.